Yes, I'm grade 12. Good morning, how are you? This is Kamala here, educator, tutor, mathematics and physical sciences, grades 10 to 12, here at College Pulukwani. Yes, so here we say, math and science made easy for you to understand. Here today we're looking at this memorandum for 2025, and this is chemistry. And in this video one, we're looking at multiple choice question 1. Question 1. They say here that which one of the following is the name of the functional group of propanol? Which one of the following is the name of the functional group of propanol? Now, propanol is an alcohol. Okay, it's an alcohol, and being alcohol, its functional group is known as hydroxyl. So the answer is C. Okay. Now hydroxyl is for the alcohols, then the carbonyl, the carboxyl is for the carboxylic acids, okay, and then the carbonyls is for the ketones, okay. Are we together? Then the formyl is for the aldehydes. So please know your theory, okay. Know your theory. The hydroxyl is for the alcohols. So these alcohols, and as you can see, when we're naming alcohols, we end with the OL, propanol, propanol. That's what the answer is. See here. Okay, 1.2. The organic compound C2H2 is converted to an alkane as shown by the reaction below. So this C2H2, as you can see, it conforms to CN, okay, H2N, CN, H2N, and this one it is for the alkenes, right? So it is an alkene here. Now the alkene, because of two carbons here, it is the ethane. Now this ethane here, because we want to get an alkane in here, saying to get an alkane, we add hydrogen, okay, and then to give us the alkane, which is the ethane, that is H3, and even here CH3, okay. So now here, they say which one of the following is a suitable catalyst. Suitable catalyst here. Now here, because we are adding an alkene with the hydrogen, we use what we call as the platinum catalyst. So here the answer is B. We use what? Platinum catalyst. We don't use lead, we don't use iron, and the hydrogen here, it is just a reactant. As you can see here, it's a reactant which is used in this reaction. So this reactant here, in this reaction, so the best answer here is platinum. So platinum is our catalyst which we use in this case. So the answer is B here. Hope we are together. And this one is called addition reaction. That's general. And because we're adding hydrogen, we call it hydrogenation. Let us proceed. Next question here. 1.3. They say, which of the following statements always apply to compounds that are structural isomers of one another? Now, what are structural isomers? Now, structural isomers, these are organic molecules which have the same molecular formula but different structural formulae. So they say here that they belong to the same homologous series. Now, this one is not correct because some structural isomers are not of the same homologous series. For example, those which we call as functional isomers like carboxylic acids and the esters, those are different homologous series, but they are functional isomers. Okay, even ketones and aldehydes, they're also isomers which we call functional, and they also have what? Different homologous series. So this answer is not correct here. Okay. Then they say they have the same structural formula. Now this one here, now we have said that the isomers, these are organic molecules that have the same molecular formula but different structural formula. So this is not correct here as well. Okay, it's not correct. And so the best answer is gonna be what? The answer is this one here. They have the same molecular formula. By the way, for your information, we have got three types of isomers, or you can call them structural isomers. One type is called chain isomers. And with chain isomers, these are organic molecules which have the same molecular formula, but a different type of the continuous chain. And then another type is called the positional isomers, whereby these are organic molecules having the same molecular formula, but different position of either the functional group or the branch. And then lastly, we have what we call as the functional isomers, whereby these are organic molecules which have the same molecular formula but a different homologous series or different functional groups. Okay, so that's not the answer. So the answer here is A. Hope we are together. Okay, let us proceed here. 1.4. They say magnesium ribbon of mass 2 grams react with the excess hydrochloric acid of concentration 0.1 mole per decimeter cubed at 20 degrees Celsius. So here we have the magnesium solid and the Mg. Okay, they say the excess HCl, right? So we have got Mg solid here and then HCl, and then they're giving us this is the concentration 0.1, that is the HCl concentration. Then we are getting Mg chloride and hydrogen gas. Okay, so they say that which one of the following changes will not increase the initial rate? Will not the English here, will not increase the initial rate. Don't forget that our initial reaction is at 20 degrees Celsius. Okay, so they're saying that now this one here they said magnesium ribbon. Okay, magnesium ribbon here. So they said that which one of the following changes will not increase the initial rate of the reaction? So they're saying using grams of powdered magnesium. Now, because of it being powder, now we're changing the state of division here from the magnesium ribbon, okay, from the magnesium ribbon to powder. Now, the powder has got a larger surface area than the magnesium ribbon, and so this one will increase the rate of the initial reaction. So this answer is not correct because the question says which one will not increase. Then they say here increasing the temperature of HCl to 30 degrees Celsius. Now the initial temperature was 20, and from the collision theory, when temperature increases from 20 to 30, we like it to have more effective collisions and hence a higher reaction rate. So this is not correct because the question says will not increase. Then they say here using a longer piece of the magnesium ribbon. Okay. Now the initial magnesium ribbon was having 2 grams here. So if you use a longer piece, it's gonna be maybe 4 grams, Now because you're having more reactant now, it means you're gonna be having more effective collisions, and so this as well will increase the initial rate of the reaction. Then they say here double the volume of the hydrochloric acid. Now if you look at our information, the given hydrochloric acid is in excess. Okay, it is in excess, meaning that hydrochloric acid is more than enough. Okay, so even if you have the volume, it will have no increase on the initial reaction rate. So the answer is D here. The answer is D because the HCl was in excess, which means we're having too much already. So even if you double, it will not have to increase the initial rate of the reaction. Okay, so the answer there is D. 1.5, they say the following reaction reaches equilibrium in a closed container, and there is a hydrogen gas plus sulfur to give us hydrogen sulfide gas. Delta H is negative, meaning it is exothermic. Now here, they say that the reaction rate versus time graph for the reaction is given below. So here we have the reaction rate on the y-axis, then we have the time on the x-axis here. I repeat, the following reaction reaches equilibrium in a closed container. Okay, so we have hydrogen gas plus sulfur solid to give us hydrogen sulfide, and it's exothermic. They say the reaction rate versus time graph for the reaction is given below. Okay, so here we have it that now we can see that this one here, which is top here, um, is called the forward reaction. So this is for the forward reaction rate, and this is for the reverse reaction rate. Don't forget that this reaction is reversible. And what's a reversible reaction? It is one whereby after getting some product, they can be reversed to give us back reactant. So now initially we don't have the products. That's why the reversible should be from this 0 here to a 0 rate. But because we had some of the reactants, it starts from somewhere initially. Okay, then it keeps on decreasing and then keeps on increasing. Here we are attaining equilibrium here. Okay, we are attaining equilibrium here, and after attaining equilibrium here, then at time t1, what happened to give us this change here? Let us look at the given question here. What change was made to the system at time t1? Now at time t1, we can set both the forward reaction, the solid line, and then the reverse reaction rate, which is dotted. They both increase and then become constant. Now, if you look at our given equation, we have one volume, okay? This is one volume because of hydrogen, okay? This one is a solid, so we don't talk about volume here. Now it also gives us one what? One volume as well. Now because we don't have any change in volume here, it means that here to get this change here, it means they did what it said here. They say the pressure was increased at a constant temperature. The volume of the container was increased. The temperature was increased, and then more hydrogen was added to the system. Okay, so here now if they added more hydrogen to the system, then that means that from literature we are going to favor the forward reaction so as to use the added hydrogen. So this is going to be like this. In that case, we would be having a jump either on forward reaction on the forward reaction rate. Okay, but here they are both moving up. So the answer for this is not right. Then the temperature was increased. Now, increase in temperature from Le Chatelier principle, it only favors the endothermic reaction, but here both of them they are favored, so that's not the case as well. They say here the volume of the container was increased. Now, when the volume increases, because we don't have any change in the volume here, it will have no effect. Okay, then if you look at our part A, the pressure was increased at a constant temperature. Now, when the pressure increases, then the volume must decrease. And if the volume decreases from C equals to N over V, it means that the concentration of both the reactants and products is going to increase. And it's going to cause a sudden increase in both of the forward and reverse reaction rate. So the best answer here is actually A. The answer is A because we are having the increase in the concentration of both the what? The forward and reverse reaction rate. Okay. Don't forget because we are having the same volume for the reactant and products. Okay. However, if we had different volumes here, then you're going to have different changes here. Okay. Yes. Hope we are together. Let us proceed. Next question here. 1.6. They say that a hypothetical endothermic reaction is given below, that is the A gas plus B gas to give us a B gas. So you're having two volumes to give us one volume here. They say that the activation energy for the reverse reaction is 50 kilojoules per mole. Which of the following is possible for the reaction above? So I repeat, a hypothetical endothermic reaction, that is this way the endothermic reaction Okay, it's very important. So whatever we do here must conform to endothermic reaction. So here, don't forget that our endothermic reaction, if we have our thing like this one here, okay, if this is the reaction coordinate, okay, reaction coordinate here, all progress, and then here we have this other one here as our change, our enthalpy or our energy in kilojoules per mole. Okay, now because we're talking about endo, it means that energy for the reactants, okay, is lower than what energy for the products. Okay, so it would come to be like this. Let me sketch this now, and then products must be higher than reactants. Okay, so this is for the reactants here, this is for the product here. Yes, now they're saying here that the activation energy for the reverse reaction is 50. So now activation energy is the minimum energy to form the activated complex. And so they're saying it is 50. So now because it is a reverse, we're starting from here now, meaning from here up to here, this portion here, it is what? It is 50. Okay. This portion is what here? It is 50 here. And that means from the products to form this complex here, it is 50. That's what they're saying here. It is 50 kilojoules per mole. Okay. So this is activation energy, but for the what? For the reverse reaction. That one is that's what they're saying. They're saying that. Then here they say that which one of the following is possible for the reaction above? They say that the heat of reaction is positive kilojoules per mole. Now this positive here, it conforms to being endothermic here. So this is correct. Okay. Then they say the activation energy for the forward reaction is 50 degrees. Now from here, this one was it was 50 degrees per mole. Now they say that the activation energy for the forward reaction is what? Is 50 kilojoules per mole. Now the forward would be from here now. Would be from here up here. I'm using a green line here now. Now this one which you see in green is our activation energy for the forward reaction from this point here up to here. Okay. So guys, as you can see, which one is longer here? The one which is green is longer. So which means that because this one here is 50, and saying here it is they're saying it is also 50 here, not possible because these two lines are not equal. These two arrows, the red and the green, they're not equal. So this is not correct. Okay, because they're saying that that is possible, but from our given information here, we see that's not true. That's not correct. They said the energy for the activated complex is 40 kilojoules per mole. Now again, they're saying that this one, which is green, is 40. But from our given diagram, we can say the red one is 50. So this can't be less than 50. So this is not correct here. They said that the activation energy of the forward reaction is what? Is 40. Now this is not correct. We have said here. It's not correct here. Now here they said the activated complex is 40. That's not correct because from here to here must be bigger than the 50. So that's why it's not 40 here. Or this must be bigger than 40. Okay. All right. So yeah, the best answer is what? The best answer is A here because they said it's endothermic and they said that the heat reaction is 70. So we can say here this one is for the product. This for the reactants here. So the H for the product and H for the reactants, when you subtract them, it's possible. It's possible here. You can get what? You can get the 70 because it's endothermic. So the best answer here is A. Let us proceed here. 1.7. They say the products of reaction below are between metal oxide and an acid are the products of the reaction between a metal oxide and an acid are. Now, when you react a metal oxide and an acid, what do we get? The metal oxide and an acid, it gives us a salt and a water. It gives us what? A salt and water here. Okay, now to get a salt and hydrogen, that's react the metal with water. But here we are reacting a metal oxide with the acid. So here we are getting salt and water. It's not correct here. Repeat. To get a salt and hydrogen gas is when we react water with a metal. Okay, and then to get a salt and carbon dioxide, you must be having a carbonate somewhere reacting with the acid, but there's no carbonate here. There's no metal carbonate here. That's not correct. They say salt, water, and carbon dioxide here. Again, here there's no metal carbonate, so the best answer here is going to be A. The answer here. Hope we are together. And the next question here, they say 1.8. The concentration of each of the four solutions below is 0.1 mole per decimeter cubed, meaning the same concentration. Okay, so here it is 0.1, everywhere it is 0.1 mole. Okay, then they say that here, which of the following correctly places the solutions in order of increasing pH? Now, increasing pH, we know that the pH gets from what? Begins from the strongest acid until the strongest base. Okay, so for this matter here, it means that in this case, if I may just remind you here, so our pH here it is in the middle, that's 7, that's neutral, 7 here. The more you go this side here, the stronger the acid. In this side here, it is what? The strongest base. Okay, so here, now this one here being sodium hydroxide is a stronger base. Okay, and being the strongest base here around, it will be this side here. So we're gonna have sodium hydroxide this here. And then this one being a nitric acid and being a stronger acid must be this side now to the strongest acid around here. So this is nitric acid here. Okay, and then now ammonia, and ammonia is a weak base, meaning it is bigger than 7 somewhere here. Okay, and then the carbonic acid, this one here, it is a weak acid, so mean that it must be somewhere here, not far from the 7. And so because they wanted this order here, you can see it's gonna be what's gonna be we are ending with sodium hydroxide, okay, and beginning with what? With the nitric acid. So the answer is gonna be this one here. So the answer is B. The best answer here is B. That's the order of the increasing pH. Increasing pH as you go this way, the pH increases from this one here until 14. Okay, so the increasing pH. The answer is B. For more information, you can visit us on 0785222041, or you can click on the link below the video in the comments here. Let us proceed. Next question here. They say here that 1.9. They say that a galvanic cell consists of the following hub cells here. This is iron 3 ions aqueous / iron 2 ions aqueous here. Then nickel 2, then to give another nickel, so they say which one of the following statements is correct for this cell? Okay. Now to know the best statement, let us first find out what we are dealing with here. Now a galvanic cell, we know it consists of the following. We have the anode, okay, with the anode, and then the cathode, this side here, okay. And if from our given theory, the anode must be more reducing than the cathode. Okay, so if you look at what we have here now, let us look at our table and find out which is more reducing than the other. Is it the nickel or it is iron? Okay, so our table 4B here is somewhere around here. Let's get it now. Let's get it now. And it is somewhere here. It's somewhere here. Let's find out now. Our table for B. Yeah, somewhere just here. Not so far. But just here. So with this table here, the table for B, which one is more reducing than the other? Now the one which is more reducing will be from the anode. Okay, because the anode undergoes what we call as oxidation. And in oxidation we give off the electrons which are going to go to the cathode to do the reduction. So if you look at our given table here, remember we are dealing with nickel to nickel 2. Okay, let's find out here. Where is it here? Nickel to nickel 2. Where it is on here. Okay, you put an arrow here. Nickel to nickel 2. This arrow here. Okay, so above this L we have what? Nickel to nickel 2. And then next here also need the iron 3 and the iron 2, right? Let's check one more time. I think you remember that. We're talking about iron 3 and the iron 2. Okay. So iron 3 with the iron 2, where are you? Iron 3, iron 2. This is iron 3, iron 2 is on here, yes. So this is the other arrow now, which I need here. Okay. Iron 3, iron 2. Just make it red. Now, if you check here what we have, above the red arrow, we have iron 3 to iron 2. And then here for the blue, we have the nickel. If you look at this other arrow here, it talks about increasing strength of reducing agent. Increasing strength of reducing agents, meaning that this arrow is pointing up. It means that the nickel, it is more reducing than the iron 3. And so because of that, our nickel is going to constitute the anode. So this is the anode. Okay, constitute the anode here, the anode, and then so will constitute the cathode. Okay. All right. Now, after getting our theory, we come back now this side here to see our given information again here. So this cell notation, actually, like I showed you here, start with the anode and then cathode. Yeah? So our anode will be the nickel, okay, being oxidized to give us nickel 2, then salt bridge here, and then now the iron 3 is going to be it's going to be what? Yeah, the iron 3 is going to be reduced. Okay, so because iron 3 ions is aqueous, okay, here we don't put a slash but we put a comma because the same phase will be reduced to give us iron 2, okay, also aqueous. Now because they are all solutions, we need we need platinum here, which is the solid here. So this platinum here will act as our surface area for which this reaction is going to take place. Okay. Now they say here that which one of the following statement is correct for this reaction? They say that here nickel 2 is reduced to iron and the iron 2 is oxidized. So the nickel 2 is not reduced. What is reduced here is iron 3 to give us iron 2. So this is not correct here. Okay. Then they said nickel 2 is oxidized. That's not correct because we see here that it is nickel solid which is oxidized to nickel 2. It's not correct here. Okay. They say the platinum electrode at the cathode. Now you see here we've got this platinum here. So this is correct because we need this metal surface for the reaction to take place. Okay. Then they said nickel is the electrode at the cathode. Now this nickel, we know this side is for the end. Okay. So this is not correct here. So the answer here is what? The answer is C. Hope we are together. And then lastly here, question 1.10. They're saying here that The setup for the electroplating of an iron metal with the silver is shown in the simplified diagram below. So you have got the iron metal, this is the silver here, this is the power source here, this is our electrolyte here. They say which of the following combinations of the anode and the reaction at the cathode is correct. Okay, so here now at the anode we have okay. Now from our theory here, because we want to electroplate the iron metal with the silver rod, it means that the silver rod must be on the anode. Why? Because it must be destroyed as it undergoes oxidation. So here, this one should be dealt with. Like we are gonna destroy it from the silver to give us the silver ions. Okay, plus an electron. Now these ions here, they're gonna go this side of the metal. Okay, then they're gonna be reduced here. So for the iron metal, gonna be having the silver ions being reduced to give us silver. Now it is this silver here which you're going to use to coat or to electroplate this metal. Okay, so what are they talking about here now? They said that at the end we should have, don't forget that here, because this one undergoes, this must be the anode, must be the anode here. We have the silver rod, this must be now the cathode this side here, cathode, because that's where we have reduction here. They said that the anode should be, now from what we see here, anode should be having silver. So anode can only be the silver and the silver rod here. Then at the cathode, like you see, we have this one here, we're having the reduction of silver ions to silver here. So we have here, this one is a reduction here, but that's not correct here. So here we have iron being reduced, that's not correct because we want to coat it with the silver. So it is this answer here, which we have here. Here we're now reducing the silver ion to silver to be used to electroplate the iron metal. So the best answer here is what? It is this D. Hope we are together. All right. Thank you so much for watching. Catch you in our video 2. If for more videos, you can subscribe, or you can get us on this number here, 0785222041. Thank you. Bye bye.